Hey everyone, and welcome. Today we're diving deep into the Field Effect Transistor, or the FET for short. These are the tiny, almost invisible switches that are, quite literally, the engine of our modern digital world. I mean, inside your smartphone, inside the most powerful computers on the planet, there are billions of these little electronic valves, all firing away. But that begs a pretty wild question, right? How in the world do you control a powerful river of electricity with nothing but an invisible force, an electric field? That's the incredible puzzle that FETs solve, and we're about to see exactly how they pull it off. So you ready? Let's get into it. So here's our game plan. We'll kick things off with a big idea, the field effect itself. Then we'll see how these electronic valves are actually built. We're going to cover the two main types, the JFET and the powerhouse MOSFET. After that, we'll put FETs in the ring with their main competitor, the BJT, for a little showdown. And finally, we'll see how this all comes together to power, well, everything. Okay, section 1, let's get right to the core of it all. What in the world is this field effect? Simply put, a field effect transistor is a device where we use an electric field to boss around a flow of electrical current. And that field comes from a voltage. The best way to picture it is like a faucet or a valve on a garden hose. The voltage you put on the control part, which we call the gate, is like your hand turning the knob. It decides how much current, how much water gets to flow from one end, the source, to the other, the drain. Now, here's a really crucial difference between FETs and another kind of transistor, the BJT. BJTs are bipolar, which means they need both negatively charged electrons and positively charged holes to work. But FETs, they're unipolar. They're specialists. They get the job done using either electrons or holes, but never both at the same time. And trust me, that one little detail makes a world of difference in how they perform. So how do you even build one of these microscopic valves? Let's take a look at how they're made, right from the silicone up. You know, it all starts with a slice of silicon, which we call a substrate. Now, pure silicon isn't all that special electrically. The magic happens through a process called doping, where we intentionally add tiny, specific impurities. If you add impurities that have extra electrons to share, you get what's called N-type material. If you add impurities that are missing electrons, creating little positive gaps called holes, you get P-type material. This ability to precisely engineer the silicon is the foundation for everything. And that brings us to our first major type of FET, the Junction Field Effect Transistor, or JFET. And the way it works is it's really clever. Okay, so a JFET is what we call a normally on device. Out of the box, there's a nice open channel for current to flow right through. But when you apply a negative voltage to the gate, its electric field creates what's called a depletion region. You can think of this as a dead zone, an area with no charge carriers. This dead zone grows into the channel and literally squeezes it. The more negative voltage you apply, the tighter the squeeze until you completely pinch off the flow. It's like squeezing a garden hose to stop the water. Now, to really get a JFET, you only need to know two main things. First is IDSS. That's just the max current you can get when the gate voltage is 0. You know, when the hose is wide open. The second is VP, the pinch-off voltage. That's the exact negative voltage you need on the gate to squeeze the hose completely shut and stop all current. With just those two numbers, you can predict exactly how it's going to behave. And here's the beautiful part. A guy named Shockley came up with an equation for this, and the key takeaway is that this behavior is baked into the physics of the transistor itself. It doesn't matter what kind of circuit you drop it into, its basic performance, its personality, it stays the same. It's predictable. All right, let's move on to the main event, the undisputed champion of transistors, the device that really, truly made the digital age possible, the MOSFETs. The secret sauce for the MOSFET, which stands for metal oxide semiconductor FET, is right there in the name. That oxide part refers to an incredibly thin layer of silicon dioxide, which is basically just glass. This tiny insulating layer sits between the metal gate and the silicon channel, completely separating them. And the result? An unbelievably high input impedance. It takes practically zero current to control the gate, which makes it amazingly efficient. So, the most common type of MOSFET is what we call enhancement mode. And unlike the JFET, this is a normally off device. There's no channel to start with, it's just off. But then you apply a positive voltage to the gate. That electric field punches right through that thin glass layer and starts pulling electrons into the area right underneath it. And just like that, a conductive channel appears out of thin air, enhancing the area so current can flow. Turn the voltage off, and poof, the channel disappears. It's the perfect light switch. Now, to be fair, there are also depletion-type MOSFETs. They come with a channel already built in, so they can act a bit like a JFET. But the real superstar, the one that you find by the billions in every single CPU, every memory chip, that's the enhancement type. Its normally off design makes it the perfect building block for all digital logic.
So now we've met the whole FET family. But how do they stack up against those other transistors, the BJTs? All right, time for a little head-to-head comparison.
Let's break this down. The absolute biggest difference is how you control them. FETs are voltage-controlled, BJTs are current-controlled. That first point leads directly to the second one, input impedance. Because a FET just needs to see a voltage, it has crazy high input impedance. It barely draws any power to be controlled. A BJT needs a little sip of current to turn on, so its input impedance is much lower. We already covered that FETs are unipolar and BJTs are bipolar, which often makes FETs quieter for things like audio amplifiers. And while they both can provide a lot of gain, they do it differently. So after all that, why did the FET, and really the MOSFET, become the king of the digital world? Let's wrap this up by looking at the big picture. It really boils down to a few killer advantages. First, that super high input impedance means they don't mess with the circuits that are trying to control them. Second, and this is the big one for our era, they can be made insanely small. That's what lets us cram billions of them onto a single chip. That small size, plus their low power use, makes them a dream for anything with a battery. And to top it off, they're generally more stable when they get hot compared to BJTs. But, they're not perfect for everything. That super thin glass layer that makes them so great, it's also their Achilles heel. It makes them really vulnerable to static electricity. One little zap from your finger can pop a hole right through it and kill the device, so you have to handle them carefully. And for certain very, very high-frequency jobs, some BJTs still have an edge. But really, when you ask where FETs are used, the shorter list is where they aren't used. They are the logic in your computer's brain, the CPU, and its graphics card. They are the tiny cells that hold data in your RAM and your flash drives. They're in high-end amplifiers, power supplies, analog switches. They are, without exaggeration, everywhere. So here's the bottom line. The field effect transistor gave us an electronic valve that's just about perfect. It's tiny, it's efficient, and it scales like nothing else before it. We've scaled it so well, in fact, that we're now packing billions of them onto a chip, pushing silicon right to its absolute physical breaking point. And that leaves us with one heck of a question for the future. What comes next? What's the next great electronic valve going to be made of?